Hey Phys kids, Mr. C here today, and we are going to talk about Newton's law of universal gravitation, or all about sort of what gravity is, which is pretty cool. I love gravity, and I think gravity is pretty cool, and honestly, I just love this. Houston, we have a negative on that orbit trajectory. We did not make it, and we're going to talk a little bit more about how we know we didn't make it, and hopefully that joke will make sense to you by the end of this video. But gravitational force. So we know that every single particle in the universe attracts the other particle with a force that is proportional to the product of their masses and inversely proportional to the square of their distances. So the further apart these objects are, the smaller that force is going to be, and the larger these objects are, the bigger that force is going to be between the two of them. And it doesn't matter what particle it is. I mean, we're talking about atoms exert this force on each other, people, planets, the sun, everything in the universe that is matter exerts this force on each other. So like little mass m here attracts big mass m, and the big mass m is attracting the little mass m. The same thing we said, like we're attracting the earth and the earth is attracting us, which is pretty cool if you think about it. The way that we write this scientifically or mathematically is that we know that the force acting between those two objects is going to be G times m1 times m2 times r squared, where m1 and m2 are the two different masses. So like in this case, you could say like m1 is little m, and you could go ahead and say m2 is big M. And then r squared is the distance between the two objects. And the distance between them is the distance from the center of the two objects. So the distance from the center of the objects. So it's not like the distance from here to here. No, it's the distance from here to here. So the center of one object to the center of the other object. We have to take that into account whenever we want to like look at the force of gravity on a planet. Come on. Nope, you don't want to go? Okay. This g here is the universal gravitational constant, and g is equal to 6.67 times 10 to the minus 11. So that's just a constant that's the same everywhere in the known universe. It's the gravitational constant, and it's really, 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 really small. And the reason why it's really, really, really small, because if you think about it, if this number wasn't small, that constant wasn't small, then the attraction between like two small particles would be huge. And, we know it's not. Like, I'm not sticking to my desk that's sitting in front of me. No. Even though I am attracting my desk and my desk is attracting me, because both of our masses are small, the distance between us is small, and that gravitational acceleration is really small, that basically means that, the force isn't that noticeable. We don't notice the force of gravity between me and this desk. So let's say, though, we have a 200-gram pickle next to a 345-gram sandwich on my plate. Oh, yes. We know that the center of their centers, or the center of each of these objects, is 4.5 centimeters apart. So like from here to here, about 4.5 centimeters. And we want to determine the force of gravity acting on the pickle, or the pickle pulling the sandwich. So we want to know what that force is that the pickle is pulling on the sandwich. Well, I don't know why this is not working. We know that the force of gravity is equal to G times M, all divided by R squared. Now, if we go ahead and plug in our numbers here, we know that that force of gravity is equal to our gravitational acceleration, or not gravitational acceleration, sorry, the universal gravitational constant, the mass of our pickle times the mass of our sandwich divided by the distance between them squared. And because our universal constant here is in SI units, we must always, anytime we use that constant, we must convert our masses into kilograms, and our distances into meters. Otherwise, we're not going to get the right answer. And we actually find that the force between these two objects is 2.3 times 10 to the negative 9 newtons. And that's really, really small. So even though that force is there, they're not going to notice each other pulling on them. And even we could go even a step further and find out what the acceleration is. Well, the acceleration is going to be that divided by their mass, which is a really, really small number divided by a really, really big number in this case. And that means the acceleration between the two is going to be so incredibly tiny. It's going to be basically zero. We won't actually see it at all. But it is still there. You might ask yourself, though, we already have this equation for the force of gravity, and we do have an equation for the force of gravity on Earth. We know that the force of gravity on Earth is m times g. However, that really only works whenever we are really, really close to the Earth's surface. The further away from the Earth we get, the gravity is actually going to get smaller and smaller. So, like, as you get up in the air and as you get up into space, gravity just kind of gradually disappears. And we're going to show you, I want to show you kind of how. So, we know that the force of gravity is equal to mg, and this is the force of gravity on an object that is on a planet. So we have to be on the planet to feel that force. But let's say we don't know what the value of g is on a planet, but we know how much the planet weighs and what the radius is. And this is actually common. Like whenever we go out and we study planets and stars and stuff, we can actually tell based on their orbits, based on how fast they're moving, based on, in some cases how much light they're emitting or what they're made up of. We can tell what their mass is and we can see what their radius is. And that can actually allow us to calculate what gravity is going to be like on that planet. So we know that the force of gravity is equal to that gm times m all divided by r squared. In this case, big M is going to be the mass of the planet, and little m is going to be just like the mass of something on the planet. We also know that the force of gravity on a planet itself is equal to that mass of the object times the gravity of the planet. These forces must be equal to each other. So we can go ahead and say, well, it's the same force, so they're equal to each other. But we see here that mass cancels out, or this little mass cancels out. So the force of gravity on a planet is going to be equal to the gravitational constant times our big mass, or the mass of the planet, times r squared, or the distance from the center of the planet to wherever the object is. And the reason this r squared is important is because at the surface of Earth, at the surface, when this r is the radius of Earth itself, g is equal to 9.8 meters per second squared. But as we start going above Earth and we get all the way up into like the stars or where our satellites are, this r is much, 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 much larger, which means that the force of gravity, whenever you're way up in the satellite or the International Space Station, is going to be much smaller than 9.8, which is crazy to think about. So now, whenever we think about stuff like this, though, we just have to notice that g equals 9.8 is only true when we're on the actual planet. Anytime we're above the planet, significantly above the planet. I mean, you have to be hundreds of meters up above the planet for this to start taking an effect. But anytime we're above the planet, g is no longer 9.8. It's actually going to change based upon the radius of the planet itself. Come on. So we have a problem here. We say that we have a hypothetical planet that has a mass that is 1.66 times that of the mass of Earth, but it has the exact same radius, and we want to know what g is near the surface. Well, if we go back, we learned that mg on that previous slide is equal to the gravitational acceleration times the mass of the object times the big mass, all divided by r squared. Or in this case, we know that g is equal to g times the mass of the planet over r squared. And if we look at this, we know that our mass of our planet is equal to 1.66 times the mass of Earth. And we know that the radius of our planet is just equal to the radius of Earth. So if we go ahead and plug that in, we know that the g of our planet is going to be equal to our gravitational acceleration times 1.66 times the mass of Earth, all divided by the radius of Earth. However, if we take a close look at this, we can rewrite it. I'm going to rewrite it as 1.66 times g times the mass of the Earth over the radius of the Earth. If we look at this here, that's actually equal to the g of Earth. So we can actually go ahead and say here, well, the g of our planet is going to be equal to 1.66 times the gravity of Earth, or we're going to be at 1.66 times 9.8, and we would have a gravity of 16.268 meters per second squared. That would be what our acceleration due to gravity is, which is pretty crazy. Okay. So how does this connect to circular motion? Well, we have to look at satellites. So a satellite is kept in a circular orbit by the speed and the force of gravity that's keeping it in circular motion. So we have to have some speed, and because of that speed, and we're traveling around the Earth, we have circular motion, which means that it's continually falling because it's accelerating down toward the Earth. At the same time, because of its velocity, it's traveling around in a circle, which is pretty crazy because as it falls down, the Earth sort of curves away from it. Okay, come on. So I want to know, what is sort of the speed of the satellite that we would have to have in order to keep it in orbit at some distance r away from the Earth. So if I wanted to find that, I know that the only force acting on this object is the force of gravity, which is equal to g times the mass of the planet times the mass of the satellite, which I'll do as ms, all over r squared. I also know, though, that because this is uniform circular motion, our net force, which is equal to Fg in this case, must also be equal to mass times our centripetal acceleration. Or if we write this, we know that the mass of the satellite times v squared over r must be equal to g times the mass of the planet times the mass of the satellite all over r squared. Now we say, well, what's the velocity? Well, if we look here, mass cancels, so it turns out the mass of the satellite doesn't matter, which is kind of weird and interesting. And one of our r's is going to cancel here too. And we find that our velocity is actually going to be equal to g times m divided by r, the square root of g times m over r. And that's the critical speed for orbit. So if we want to send something to orbit around the Earth at a certain distance or a certain radius from the center of the Earth, we must give it a velocity of gm over r. Anything bigger than that, and it's actually going to go flying out of orbit, or it'll move to a higher orbit. And anything smaller than that, it's going to come crashing back down to Earth, which would not be good at all. Well, I mean, maybe you want that. I wouldn't want that on the world, though. Okay. So now we have to say we want to determine the speed of a GPS satellite that's orbiting at the height of 2.07 times 10 to the 7 meters above the Earth. And in this case, we know that the radius of the Earth is 3.8 times 10 to the 6 meters, and the mass of the Earth is 5.98 times 10 to the 24th. So we want to determine that speed. So we found, or we realized earlier, that that maximum or that critical speed is going to be equal to the square root of the mass of the planet times the gravitational constant divided by the radius of the planet. Not the radius of the planet, but the radius of the object to the planet. So in this case, if this is like Earth, that's the radius of Earth, and this is our satellite. What we want is this radius here. It's the distance from the center of the Earth to our GPS satellite. So that's what this r is talking about here. So our centripetal acceleration is actually going to be equal to, in this case, the mass of the Earth times g, all divided by the radius of the Earth, plus that 2.0 times 10 to the 7th meters. And when we plug that all into our calculator, we can find out what our critical speed is. But remember, the tricky thing here is we know that the radius that we're talking about is the distance from the center of the Earth to the satellite. It's not the distance from the Earth to the satellite, it's the distance from the center of the Earth to the satellite. Our next question is, what is the centripetal acceleration of the satellite? Well, if we want to define centripetal acceleration, we know that our centripetal acceleration is just equal to v squared over r, which in this case we take v squared, which would just be me times g over re plus 2.0 times 10 to the 7th, divided by our radius, which is also re plus 2.0 times 10 to the 7th. And that's going to give us our centripetal acceleration, which is pretty awesome. But now what I want you to do is I want you to go ahead and I want you to fill out the video check. And we will talk more about gravitation, and I see you in class next. Have a great day.